So section 2.6 is combinations of functions. And before we can start looking at different ways that we can combine functions, we need to review the domain of a function. In sections 2.1 and 2.2, we looked at graphs of functions. And from looking at the graph, we were able to determine the domain. But now we're going to move to being able to determine the domain of a function by looking at its function definition. And if a function f does not model data or verbal conditions, its domain is defined to be the largest set of real numbers for which the value of f of x is a real number. Remember that in some of the problems that we were looking at with respect to quadratic applications, we had to limit the domain because it didn't make sense, for instance, to talk about negative time, right? So if that's not the case, if we're just looking at a function definition without any verbal conditions attached to that particular function, then the domain is going to be that largest set of x values for which f of x is a real number. And at this point, before we get to chapter 4, the only two things that we're going to be concerned about are division by zero. So we're going to exclude from a function's domain real numbers that cause division by zero, and taking even roots of negative numbers. Because division by zero is undefined, and taking even roots of negative numbers results in imaginary solutions, right? And we don't want either one of those things to happen because those aren't going to be real numbers. So let's go ahead and look at some examples. And remember, we're going to be looking for two things. Could any value of x cause division by zero? And could any value of x cause us to take an even root of a negative number? In the case of either one of those, we're going to exclude those x values. The first couple of examples involve linear and quadratic functions. So if I'm looking at f of x equals negative 5x plus 4, there is no way that we're going to end up dividing by 0 here, and since there's no radical signs, there are no values of x that need to be restricted. So the domain on this particular function is going to be all real numbers. In fact, any polynomial is going to have a domain of all real numbers. Now, in order to show that using interval notation, which is what you're going to need to do in the homework, that's going to be from negative infinity to positive infinity. Part B is a quadratic function. We know the domain of that is all real numbers. Part C is another quadratic function. The domain is all real numbers. But when we get to part D, we get to the first one where we have to give a little more thought to this particular problem, right? Because I notice that I have a square root sign, which is an even root. And so what is under this radical is not going to be allowed to be negative, right? Because we don't want an imaginary outcome. So I need for that radicand, that expression under that square root sign, to stay greater than or equal to 0. And if whatever I input for x results in x minus 3 being greater than or equal to 0, then the square root will be a real number. Now, in order to solve this inequality, all I need to do is add 3 to both sides, and I will get that x has to stay greater than or equal to 3. And then if I'm looking at a number line, 0, 1, 2, 3, that's going to be a closed circle because I'm including the value of 3, and everything to the right towards positive infinity. And recalling that a closed circle results in a bracket in interval notation, that's going to be from 3, including 3, to positive infinity. Now, what about this next one? F of x equals the square root of the opposite of x plus 4. Well, I need the opposite of x plus 4 to remain greater than or equal to 0. And so I have several options here. I could go ahead and let's do this. Let's do it this way first. We could subtract 4 from both sides. I'm going to end up with the opposite of x is greater than or equal to negative 4. And then I need to divide both sides by negative 1. And remember that when I am dividing an inequality by negative 1 or multiplying an inequality by negative 1 or any negative number for that matter, I have to change the direction of the inequality sign. So I'm going to get that x is less than or equal to positive 4. And if I think about my number line, 0, 1, 2, 3, 4, that's going to be a closed circle on 4, pointing to the left towards negative infinity. And so my domain in interval notation for this one is going to be from negative infinity to 4. Now, the next one, the square root of 3x minus 12, I need for that expression under the radical sign to be greater than or equal to 0. So I can go ahead and add 12 to both sides. 3x is greater than or equal to 12. Divide both sides by 3. X is greater than or equal to 4. And so on a number line, 1, 2, 3, 4, that's a closed circle pointing to the right towards positive infinity. So the domain is going to be bracket for comma positive infinity in interval notation. So to summarize what we did on the left-hand side of these examples, any polynomial function is going to have a domain of all real numbers from negative infinity to positive infinity. If I'm dealing with a square root, I need the expression under the radical sign, the radicand, to stay strictly greater than 0. Now on this right-hand side, we're looking at some rational functions, meaning that we're dealing with fractions. And so I'm going to have to deal with these slightly differently, right? So we've looked at the concern of taking even roots of negative numbers with examples D, E, and F, and now we're going to look at the concern of division by 0 with the examples on the right-hand side. So when I look at example G, I see that 4 is divided by x minus 6. Since there is a variable in the denominator, I need to be concerned about division by 0. And for these, I'm going to go about it a slightly different way. I'm going to be saying that I need for x minus 6 to not be equal to 0. So I'm going to solve for the restrictions by saying what values of x would cause it to be equal to 0. X minus 6 equals 0 is going to tell me what my restrictions are going to be. Well, solving that, I'm going to add 6 to both sides, and I get that x is equal to 6. Whoop. So that is a restricted value. So I'm going to come over here to my number line. 1, 2, 3, 4, 5, 6. And I'm going to put an open circle on 6 because x is not allowed to be 6. Now, since that is the only restricted value, it can be anything less than 6 down towards negative infinity, anything greater than 6 off towards positive infinity. And let me use two different colors here. So I'm going to anything less than 6 or anything greater than 6. So when I'm thinking about that in terms of interval notation, everything on this left side that is in green, right, is going to be part of my domain. So from negative infinity up to but not including 6. And on this right-hand side in red, starting but not including 6 towards positive infinity, right? So these two disjoint intervals, these two different separate parts of my real number line, right? So what I'm saying is anything in the interval from negative infinity up to but not including 6, or not including 6 proceeding on towards positive infinity. And the way that I say or using interval notation is a union sign. So my domain is going to be from negative infinity up to but not including 6, union, starting but not including 6, up towards positive infinity. And that is how you're going to have to answer the domain questions in the homework assignment for this section. All right, so moving on to a slightly more complicated problem. We see we have x squared minus x minus 6, and I'm going to be solving for my restrictions. By setting that quadratic equal to 0 and finding the two values of x in this case that will result in 0 in my denominator. And I can see that this one's going to factor because two numbers that multiply to give me negative 6 and add to give me negative 1 are negative 3 and positive 2. So either x minus 3 equals 0 or x plus 2 equals 0. Solving this is going to give me x equals 3. Solving this one's going to give me x equals negative 2. So looking at my number line, and for these particular problems, drawing a number line is really helpful. Here's 0, negative 1, negative 2, 1, 2, 3. I'm going to place open circles on negative 2 and positive 3. And those are the only two values on that real number line that have to be excluded from my domain. So then I've got a piece that is going to be on this left-hand side of negative 2. There's going to be this interval between negative 2 and 3. And then I'm going to have this interval to the right of 3. And so this piece on the left of negative 2 is going to be from negative infinity to negative 2, not including the negative 2. Again, union. And then from negative 2 to 3, excluding both endpoints, union, 3 to positive infinity. And so that color coding kind of helps us out, right? The domain is from negative infinity to negative 2, union, negative 2 to 3, union, 3 to positive infinity, which is quite a long, drawn-out way of saying x is not allowed to be negative 2 and x is not allowed to be 3. But it's this interval, the union of these three disjoint intervals on that number line is going to be the domain for that particular function. Example I is yet another quadratic in the denominator, and solving for the restrictions. We know that x squared minus 9 equals 0 will give me my two restrictions. I can go ahead and add 9 to both sides. X squared equals 9. And then use my square root property to solve for x equals positive or negative square root of 9, or x equals positive or negative 3. Or you could factor it as the difference of perfect squares as well. The two excluded values on my number line are going to be negative 3 and positive 3. So looking at that, I'm going to have everything to the left of negative 3, everything between negative 3 and 3, and everything to the right of 3. And so my domain is going to be from negative infinity to negative 3, union, negative 3 to positive 3, union, positive 3 to positive infinity. All right, one more example. In J. And this one is just to remind us of our factoring. Again, my restrictions are going to come from solving x squared minus 4x equals 0. This one's not a trinomial, nor is it a difference of perfect squares, but I do notice that I have a common factor of x. So I'm going to go ahead and factor out an x, and then I'm going to have x minus 4 equals 0. Check my distributing to just redistribute to check my factoring. X squared minus 4x. So either x is equal to 0 or x minus 4 is equal to 0. So in this case, x equals 0 or x equals 4. So let's see if we could go ahead and do this one without drawing the number line first. I'm going to go from negative infinity to 0, jump over the 0, from 0 to 4, jump over the 4, 4 to positive infinity. Just make sure that when you're doing your interval notation for the domain like this, that you arrange these two restricted values from least to greatest, and then it's actually quite easy to go ahead and put together your domain. All right, so I'm going to go a little bit out of order. I'm going to skip down to example L, and then I'll come back up to K. So when I'm looking at example L, solving for my restrictions, x squared plus 4 equals 0. And that's a sum of squares, which I know does not factor over the reals. In fact, if I try and solve it using the square root property, I'm going to be solving x squared equals negative 4. So x equals the positive or negative square root of negative 4, positive or negative 2i, which are both imaginary. And so there are no real numbers that could serve as an input to this particular function that would cause me to have 0 in the denominator. If you think about it, if you square a real number, it's always going to be greater than or equal to 0. And any number that's greater than or equal to 0 plus 4 is never going to be 0, right? So my domain has no restrictions. In fact, it is from negative infinity to positive infinity. No restrictions on this one. All right, so let's go back up to K, because this one is just a little bit different, right? I have a radical and a variable in the denominator, so I have two issues. Now, I'm going to go ahead and solve for the domain instead of solving for the restrictions by noting that if I was solving, if it was just the square root of 2x minus 8 and I was finding its domain, I would need for 2x minus 8 to be greater than or equal to 0. Because that radical is in the denominator, I have to remove the possibility of it being equal to 0, right? So if I solve this inequality, 2x minus 8 is strictly greater than 0, then I will be taking care of both the possibility of imaginary roots and division by 0. So now I'm going to go ahead and finish solving my inequality. So 2x is greater than 8. Divide both sides by 2. X is greater than 4. So when I'm thinking about my number line now, 1, 2, 3, 4, I'm going to be putting an open circle instead of a closed circle on 4. And my domain is going to be from 4, parentheses, right, to positive infinity. Now that we've reviewed how to find the domain of a function given its function definition and not its graph, we can go on to objective 2, which is to think about combining functions using the algebra of functions and specifying the domain of those combined functions. We can combine functions by adding, subtracting, multiplying, and dividing the algebraic expressions that appear on the right side of the equations. And by performing these operations on functions, we will be creating new functions. So we're not going to be solving in this particular objective. We're just going to be creating new functions. So if we let f and g be two functions, the sum f plus g, the difference f minus g, the product f times g, and the quotient f divided by g are new functions whose domains, that should say functions, whose domains are the set of all real numbers common to the domain of f and g. So now the way that we define the sum of two functions is really very straightforward. F plus g of x is simply equal to f of x plus g of x. The difference, f minus g of x, is simply f of x minus g of x. The product, f times g of x, is simply f of x times g of x. And the quotient, f divided by g of x, is simply f of x divided by g of x. And of course, we have to take into account that g of x is not going to be allowed to be equal to 0. And I have here bolded, underlined, and not italicized, but capitalized. Note, we are not solving for x. We are using arithmetic operations to form brand new functions. So let's look at a couple of examples. In example 2, we're going to find the sum, difference, product, and quotient of these two functions. F of x is 2x plus 1. G of x is x squared minus 4. So if I want to find f plus g of x, this is simply going to be equal to f of x plus g of x. So 2x plus 1 plus x squared minus 4. Now those parentheses are not really serving a purpose for me, so I can go ahead and remove them. 2x plus 1 plus x squared minus 4. And all I need to do is combine my like terms. I have an x squared. I have a 2x. And then I have 1 minus 4, which is negative 3. So f plus g of x is the new function, x squared plus 2x plus 3. And we are going to stop because we are not solving anything. We're just finding a new function. Now, because this is a polynomial, the domain is going to be all real numbers. There are no radicals, there are no variables in the denominator. Now, f minus g of x, the only thing that we have to be mindful of here is because we are finding f of x minus the entirety of g of x, we need to use our parentheses, and we need to make sure to distribute this negative sign across all of g of x, right? And that's the biggest mistake that students make with the difference of functions. So now I'm going to have 2x plus 1 minus x squared plus 4. Be very careful with your sign there, right? So now this is going to be equal to negative x squared plus 2x plus 5. Again, stop. We have found the difference, which is a new function itself. Polynomial again, domain, all real numbers. Now we're going to find the product, f times g of x, which is, of course, f of x times g of x, which is going to be equal to 2x plus 1 times x squared minus 4. And all I need to do here is carry out my multiplication by distributing, right? So 2x times x squared is 2x cubed minus 8x plus x squared minus 4. There are no like terms. The only thing I might do is just go ahead and rearrange so that I have descending powers of my variable. It's not technically necessary, just looks prettier. 2x squared plus, 2x cubed plus x squared minus 8x minus 4. I have a third degree polynomial, so the domain is, again, all real numbers. And finally, the quotient, f of x divided by g of x. So 2x plus 1 divided by x squared minus 4. And at this point, I'm going to go ahead and I'm going to factor my denominator because I need to find the domain of this function before I simplify. And so first thing I'm going to do is factor my denominator, 2x plus 1 divided by x plus 2 times x minus 2. That's a difference of perfect squares, right? And so my domain is going to have two restrictions. Found by solving x plus 2 times x minus 2 equals 0. So either x plus 2 equals 0 or x minus 2 equals 0. Subtracting 2, x minus 2, adding 2, x equals 2. So looking at my number line, negative 2, 0, 2. I'm going to have open circles on negative 2 and 2. Those are the two restricted values. So my domain is going to be from negative infinity to negative 2, union, negative 2 to positive 2, union 2 to positive infinity. I mean, just draw an arrow and put that right there, right? And now after, and only after, I have answered my domain question, then I turn to asking myself if this particular function will simplify. And because I do not have any common factors, this is in simplest form. I could leave it like this, or I could type it in like this when I'm doing my homework in my math lab, and we have finished that particular problem. Now another example. With f of x equal to 2x squared minus 7x minus 15, and g of x equal to x minus 5. So again, to find the sum, that's going to be equal to f of x plus g of x. So 2x squared minus 7x minus 15 plus x minus 5. No need for the parentheses. I'm only putting them to get us in the habit of using them because often they are necessary. And now combining like terms, we've got a 2x squared negative 7x plus 1x is minus 6x. And then negative 15 minus 5 minus 20. Again, stop. Don't set that equal to 0 and start solving things because all we're doing is finding the new function that is determined by combining f and g using addition. Because this is a polynomial, the domain is going to be all real numbers. Now, f of x minus g of x, we start to see why those parentheses are important, right? 2x squared minus 7x minus 15 minus the quantity x minus 5. Again, I have to distribute. So I'm going to end up with 2x squared minus 7x minus 15 minus x plus 5. If you're getting it wrong in the homework, then make sure that it's very well could be that you're forgetting to distribute that across that binomial. Now, combining like terms, I'm going to have 2x squared minus negative 7x and negative 1x is minus 8x. And then negative 15 plus 5 is minus 10. Again, domain, all real numbers because I'm looking at a polynomial. And all I'm doing is finding that new function. F times g of x is f of x times g of x, or 2x squared minus 7x minus 15 times x minus 5. It's a little easier to distribute if you put the binomial on the left because multiplication is commutative. Doesn't matter what order I do it in. And now I'm going to think about multiplying each of these terms times x, and then each of these terms times negative 5. So 2x squared times x is 2x cubed. negative 7x times x is negative 7x squared. Negative 15 times x is minus 15x. Now I'm going to come back through and multiply everything by negative 5, and I'm going to line up my like terms. So negative 5x times negative 5x times 2x squared is negative 10x squared, lining up my like terms. Negative 5 times negative 7x is plus 35x. And then negative 5 times negative 15 is plus 75. So I'm going to end up with 2x cubed minus 17x squared plus 20x plus 75. And of course, it's another polynomial, so my domain is all real numbers. And then finally, f divided by g of x is f of x divided by g of x, or 2x squared minus 7x minus 15 divided by x minus 5. In this one, I'm going to have one restricted value, right? Because if I solve for my restrictions on this one, x minus 5 equals 0, add 5 to both sides, my restricted value is x equals 5, right? And so my domain is going to be from negative infinity to 5, union 5 to positive infinity, right? That number line is going to include every value except for 5. So from negative infinity up to, but not including 5, jump over the 5, not including 5 on to positive infinity. Now this one is a bit different because I need to think about whether or not, now that I've answered my domain question, which I always answer first, whether or not this will simplify. And in order to make that decision, I need to factor this numerator if possible, right? So I'm going to come over here, 2x squared minus 7x minus 15, and think about factoring it. I can either use the trial and error method, guess and check, or I can use factoring by grouping. I'm going to go ahead and use the factor by grouping method. So in order to do that, and if you need a refresher on this, go back to the review materials and factoring polynomials. I'm going to multiply a times c, 2 times negative 15 is negative 30. I'm going to be looking for two numbers that multiply to negative 30 and add to negative 7, right? And I'm thinking that it's going to be 3 and 10, right? So if I use a positive 3 times a negative 10, that multiplies to give me negative 30, and positive 3 plus negative 10 is equal to negative 7. And then I'm going to rewrite my middle term using those two numbers, plus 3x minus 10x minus 15, and then I'm going to use grouping, right? So I'm going to group the first two and the second two. The only factor those first pair have in common is x, 2x plus 3, minus, common factor is a 5, negative 5 times what gives me negative 10x? 2x. Negative 5 times what gives me negative 15? Positive 3. I'm going through this kind of quickly, and if you need to go back and review and refresh, there is that review material in Blackboard. Common binomial factor of 2x plus 3. And I am left with x minus 5. So now I can come back up here and note that this is 2x plus 3 divided by x minus 5, all divided by x minus 5. And I notice that, in fact, I do have a common factor. X minus 5 is a factor in my numerator, and x minus 5 is a factor in my denominator. So those x minus 5s are going to divide out, leaving me with 2x plus 3. And so if I do this problem in my math lab and I type in this answer for the quotient, it's going to tell me, although your answer is correct, it's not in simplest form. You need to go on and factor and simplify. If it asks you for the domain and you use the domain of the simplified version, all real numbers, that's going to be wrong as well. The domain includes the original function's restrictions, all right? So x cannot be 5, and the simplified version is 2x plus 3. And so in terms of this algebra of functions, one like this would be probably the most complicated one that you're going to see. Now we're going to look at objective 3, to find and simplify a function's difference quotient. And this is actually taken from, I pulled it from section 2.1 and brought it into this section because it does deal with the difference of two functions. And I thought it was a better placement of this topic in section 2.6. You will not need to memorize the difference quotient, but you will need to be able to evaluate the difference quotient for a given function. This is a very important expression in calculus, and because college algebra is a preparation, a prerequisite course for both business calculus and engineering calculus, you need to have this expression and how to simplify it in your math toolbox as you head into those two classes. So what the difference quotient looks like is f of x plus h, which we did a bit of work with in section 2.1, right? F of x plus h minus f of x, all divided by h, where h doesn't equal 0. This is called the difference quotient. So now we're going to go ahead and do a couple of examples of this. Example number 1, find and simplify the difference quotient for f. F of x equals 2x plus 3. So I'm going to go ahead and write the difference quotient, and I'm going to use two different colors. F of x plus h minus f of x, all divided by h. So remember that f of x plus h is simply following the rule for f, plugging in x plus h in the spot where the input goes, right? So following the rule, 2 times the input, x plus h plus 3 minus, parentheses, critically important here. Please make sure that you're using these parentheses or you're going to get these wrong. F of x is 2x plus 3. And this is all divided by h. So now we need to distribute, and we're going to get 2x plus 2h plus 3. We need to distribute, and if there's going to be an issue, it's usually with the signs here. Minus 2x minus 3, all divided by h. Now, if you are doing the difference quotient for a polynomial, then anything in the numerator that doesn't have an h should cancel out. Okay, for polynomial functions, this will be true. So 2x minus 2x, 3 minus 3. So I end up with 2h divided by h, and the h's are going to divide out, 1, 1, right, to leave me with 2. So my difference quotient for this particular function is equal to the constant 2. And if you remember your work with graphing lines, and this would be a line, right? The general form for a line, or we talk about slope-intercept form, right? Y equals mx plus b. When you evaluate, find and simplify the difference quotient for a linear function, it'll always be equal to the slope of that line. So that's a good way to know if you're on the right track with finding the difference quotient for a linear function. But now, what about a quadratic function? F of x equals x squared plus 2x plus 1. Again, I'm going to use my colors. So I'm going to have f of x plus h minus f of x all divided by h. So now, when I am finding f of x plus h, I need to follow the rule. Input squared plus 2 times the input plus 1, right? So the input is x plus h squared plus 2 times the input x plus h plus 1 minus, in parentheses now, x squared plus 2x plus 1 all divided by h. And I need to be careful with this expression particularly because it's x plus h quantity squared, right? And let's just take a minute to review on how that should be done, right? X plus h quantity squared is x plus h times x plus h. So when I distribute, I'm going to get x squared plus xh plus hx or xh plus h squared. X squared plus 2xh plus h squared. So be really careful when you're expanding this square that you don't forget that you're going to have middle terms, right? So I'm going to end up with x squared plus 2xh plus h squared, distributing here, 2x plus 2h plus 1 minus, distributing here, be careful with these signs, minus x squared minus 2x minus 1 all divided by h. And then again, this is a polynomial, so anything that doesn't have an h should cancel out. X squared minus x squared, 2x minus 2x, 1 minus 1. And I'm going to end up with 2xh plus h squared plus 2h, all divided by h. Okay, so we're well on our way, but the last thing we need to do is simplify this. And I notice that there is an h that is a common factor to all the terms in my numerator. So I'm going to go ahead and factor that out. I'm going to have 2x plus h plus 2, all divided by h. And then those are going to divide out, right? And I'm going to be left with 2x plus h plus 2, which is the simplified version of the difference quotient for this quadratic function. Now, the nice thing again about this being a video lecture is if you got lost anywhere in this process, you can back up the video and watch it again as many times as you need to get comfortable with this. You're going to have a couple of problems like this in the homework, so you might need to come back and re-watch the video for this, right? It is an important skill set that you need if you're going on to business calculus next or eventually to engineering calculus. The last objective for this section is to form composite functions. Another way to combine functions is called composition of functions. And often we come across situations where one quantity is a function of a second quantity, and that depends on a third quantity. And the example from our textbook involves Nielsen ratings. For example, the cost of advertising on a television show may be a function of the Nielsen rating of the show. The Nielsen rating, in turn, is a function of the number of people who watch the show. So, in the final outcome, the cost of advertising may be affected by the number of people who watch the show. So if you think about it, you're going to have the number of people who watch, right? Number of people. That's going to give you a Nielsen rating. And then that's going to give you the cost, right? So the cost is ultimately partially a function of the number of people who are watching the show. Now, how do we show this in an algebraic context? Well, the composition of function f with g is denoted by f little open circle g, right? That's not a multiplication sign, it's a composition sign. And you read this as f of g, f of g. So you can think about that little open circle as being like the O in the word of. And it's defined by the equation f of g of x is equal to f of the g of x, right? So what's going to serve as the input to my function f? My function g, right? And we're not going to worry too much about the domain of composite functions, but it is the set of all x such that x is in the domain of g and g of x is in the domain of f. So let's look at some examples of this. For f of x equal to 3x minus 4 and g of x equal to x squared plus 6, let's find the following functions. F of g of x. Now, I go through a very specific set of steps as I'm finding these compositions, and I would suggest you do the same because it really helps you keep on track. So I'm going to rewrite this as f of g of x, and then I'm going to rewrite it again as f of, well, what is g of x? G of x is x squared plus 6. So f of x squared plus 6. Now, it might help to remind yourself that the function f takes an input and says 3 times that input minus 4, regardless of what that input is, right? In this case, the input is going to be the expression x squared plus 6. So f of x squared plus 6 is going to be 3 times x squared plus 6 minus 4, right? 3 times the input, x squared plus 6 minus 4. So am I following the rule or the pattern or the template that f is defined by? Yes. F of whatever the input is, right, is equal to 3 times that input minus 4. Now I just need to distribute and simplify. So it'll be equal to 3x squared plus 16 minus 4, or 3x squared plus 14. That is the new function f of g of x. Now, if I do it in the opposite direction, g of f of x, this is going to be equal to g of, well, f of x is 3x minus 4. Now, the rule for g of the input, right, is equal to the input squared plus 6. What's the input this time? It's 3x minus 4, right? So I'm going to take, 3x minus 4, square it, and then add 6. Am I following the rule that g is defined by? Input squared plus 6. What's my input? 3x minus 4. 3x minus 4, input squared plus 6. Yes, I am. Now you have to be careful again when you square a binomial, right? Because it's 3x minus 4 times 3x minus 4. That's going to give me 9x squared minus 12x minus 12x, right, plus 16, first, outer, inner, last, plus 6. If you need some scratch paper to do that, go ahead. So now I've got 9x squared minus 24x plus 22. Now let's look at another example. For f of x equal to 2x minus 3 and g of x equal to 3x squared minus x plus 6, find the following functions. So again, I'm going to write f of g of x. F of g of x is 3x squared minus x plus 6 equals, now what is the rule for f? 2 times the input, whatever it is, minus 3. So 2 times my input is what? 3x squared minus x plus 6 minus 3. Did I follow the pattern? I did. Now I just need to distribute 6x squared minus 2x plus 12 minus 3 and combine like terms. 6x squared minus 2x plus 9. And then g of f of x. This is g of f of x is 2x minus 3. And I'm going to follow the rule or the pattern that's set forth for g. 3 times the input squared minus the input plus 6. So 3 times the input squared, 2x minus 3, minus the input, 2x minus 3, plus 6. So did I follow the rule? 3 times the input squared minus the input plus 6. 3 times the input squared minus the input plus 6. I did. So now I can go ahead and first deal with my exponent, right? So I need to square this first before I distribute the 3. That's going to be 2x times 2x is 4x squared. Outer minus 6x. Inner minus 6x. Last plus 9. Minus, distributing, I'm going to get minus 2x plus 3. Be careful about your sign there, right? Plus 6. Now, I can go ahead and combine like terms in here. 4x squared minus 12x plus 9 minus 2x plus 9, right? Now I can go ahead and distribute the 3. And I'm going to get 12x squared minus 36x plus 27 minus 2x plus 9. And now I can combine my like terms. 12x squared minus 38x plus 36. One more thing to think about with respect to composition of functions. We can also evaluate the composition of a function at a given value of my independent variable. And this is actually often much easier than what we were doing before, because what this one is asking me to do in part A is f of g of negative 1. So what it's really asking me to do is figure out what is g of negative 1 and use that as the input to my function f, right? So I'm going to come over here to the side, and I'm going to evaluate g of negative 1. G of negative 1 is 2 times negative 1 squared minus 2 times negative 1 minus 5. 2 times 1 plus 2 minus 5. 4 minus 5 is negative 1. Now that's just a coincidence that it turned out to be the same, okay? So I'm going to replace g of negative 1 with what it's equal to. This is going to be f of negative 1, because g of negative 1 is negative 1. And now I'm going to evaluate f of negative 1. Well, what does f say to do? Square the input plus the input minus 3. This time the input is negative 1. So 4 times negative 1 squared plus negative 1 minus 3. So negative 1 squared is 1. 4 times 1 minus 1 minus 3. 4 minus 1 minus 3 is 0. So f of g of negative 1 is equal to 0. And, you know, sometimes you'll see when a textbook is dealing with and explaining composition of functions, they'll show it as like two machines that are in concert, one after the other, right? So here is my g of x. So machine, in comes the input, out comes the output, and here is f of x, right? So if I put negative 1 into g of x, ka-chunk, 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 it does its work, right? Out comes negative 1. That serves as the input to f of x. It does its work, ka-chunk, ka-chunk, ka-chunk. And then out comes the output, 0, right? So it's two functions that are connected in series, right? And I'm going to find the input of negative 1 going into g. What is g of negative 1? And then the output of that goes into my function f, right? So if that helps, that visual, that's what's going on, right? Now, part B asks me to find g of f of 0. So I'm going to come over here, and I'm going to find f of 0. Well, it's 4 times 0 squared plus 0 minus 3. 0, 0, that's just equal to negative 3, right? So I am finding g of negative 3, which is equal to, following the rule, 2 times the input squared minus 2 times the input minus 5. So 2 times 9 plus 6 minus 5. 18 plus 6 minus 5 is 19. So g of f of 0 is equal to 19. And then finally, you can compose a function with itself. And you can also do composition more than once, right? So this is going to be equal to g of negative 2. So I'm going to come over to the side, and I'm going to find what is g of negative 2. So g of negative 2 is going to be equal to 2 times negative 2 squared minus 2 times negative 2 minus 5. So that's going to be 2 times 4 plus 4 minus 5. 8 plus 4 minus 5 is 7. So I'm going to be finding g of 7. And following my rule for g, it's going to be 2 times 7 squared minus 2 times 7 minus 5. So 2 times 49 minus 14 minus 5 is equal to 98 minus 14 minus 5, which is equal to 79. So g of negative 2 is equal to 79.